Just like complex powers, the Moivre's theorem in solving complex roots also follows a pattern, which makes the procedure easier. Learn about it here in Mathematics of Engineering. The Moivre's theorem in solving complex roots uses the polar form of the complex number. In such form, z raised to n comprises of the modulus r cis theta, or that is r times cosine of theta plus I sine of theta. Take for example z cubed as 8 times cosine of 60 plus I sine of 60 degrees. The complex roots of z in this complex number are z1, which uses theta as 60 degrees. The second root z2 uses the theta 60 degrees plus 1 revolution, which is equal to 360 degrees or 2 pi in radians. z3 is solved using theta plus 2 revolutions. That would be 720 degrees or 4 pi. Placing the concept into mathematical statement, the Moivre came up with the complex root as the nth root of the modulus r times cosine of theta plus 360 k over n plus I sine of theta plus 360 k over n. In case we are to use radians, one revolution of 360 degrees is replaced by 2 pi. In this theorem, n is the root and k is the number of revolutions, starting with 0 for the first root, and k is n minus 1 as the last revolution. So k starts with 0 to 1, 2, until n minus 1. Let's showcase the procedure with the first example, finding the complex roots of the complex number z raised to 4 as 16 cosine 120 plus I sine of 120 degrees. In the polar form, r is evident as 16 and theta as 120 degrees. With the argument in degrees, we use 360 for one revolution. N is 4 and k has 0, 1, 2, and 3. For the first complex root, k is taken as 0. z1 is the fourth root of 16 times cosine of 120 plus 360 by 0 over 4 plus I sine of 120 plus 360 times 0 over 4. The second term is just 0, making the argument only 120 over 4. So z1 is 2 times cosine of 30 plus I sine of 30 degrees. For z2, k is taken as 1. With the same pattern, we have z2 as the fourth root of 16 times cosine of 120 plus 360 times 1 upon 4 plus I sine of 120 plus 360 times 1 upon 4. z2 is then 2 cosine of 480 over 4 plus I sine of 480 upon 4. Simplified as 2 cosine of 120 plus I sine of 120 degrees. For the third complex root, take k as 2. Plug this into the equation and have the fourth root of 16 times cosine of 120 plus 360 times 2 upon 4 plus I sine of 120 plus 360 times 2 all over 4. The modulus and argument then turns into 2 and 840 over 4, which is then reduced into z3 as 2 cosine of 210 plus I sine of 210 degrees. For the fourth complex root, use k as 3. Z4 uses the theorem of fourth root of 16 cosine of 120 plus 360 times 3 all over 4 plus I sine of 120 plus 360 times 3 over 4. This turns into 2 cosine of 1200 upon 4 plus I sine of 1200 over 4, which can be further reduced into 2 cosine of 300 plus I sine of 300 degrees. The next example uses radians, with z cubed as 8 cosine of 2 pi upon 3 plus I sine of 2 pi over 3. R is observed as 8, and theta is 2/3 of pi. Instead of 360 degrees added to the succeeding roots, we use 2 pi in the equation, which has n of 3 and k as 0, 1, and 2. For the first complex root, k is taken as 0, so z1 is the cube root of 8 times cosine of 2/3 of pi plus 2 pi times 0 all over 3 plus I sine times 2/3 of pi plus 2 pi times 0 all over 3. The added revolution is simplified as 0, so z1 is then 2 times cosine of 2/3 of pi upon 3 plus I sine of 2/3 of pi upon 3, which is then taken as 2 times cosine of 2/9 of pi plus I sine of 2 pi over 9. The second complex root uses k as 1. Place this into the equation and get the cube root of 8 times cosine of 2/3 of pi plus 2 pi times 1 over 3 plus I sine of 2/3 of pi plus 2 pi times 1 upon 3. Create equivalent fractions to add the arguments easily, making 2 pi times 1 equal to 2 pi, which in turn is converted into 6/3 of pi. Add this to theta, which is 2 pi over 3, and get 2 cosine of 8/3 of pi over 3 plus I sine of 8/3 of pi over 3. Z2 is then 2 cosine of 8/9 pi plus I sine of 8 pi over 9. The third complex root uses k equal to 2. The equation then becomes the cube root of 8 times cosine of 2/3 pi plus 2 pi times 2 over 3 plus I sine of 2/3 pi plus 2 pi times 2 over 3. 2 pi times 2, which is 4 pi, can be transformed into 12/3 of pi to adapt to the same denominator. Then add theta, which is 2/3 pi. The equation then turns into 2 cosine of 14/3 of pi over 3 plus I sine of 14/3 pi over 3. The third complex root is then 2 times cosine of 14/9 of pi plus I sine of 14/9 of pi. The next example requires the complex roots of I. The complex number can be interpreted as 0 plus I. So the modulus is root of 0 squared plus 1 squared, which is still 1. Illustrating the vector shows that it is pointing upwards, so theta is taken as 90 degrees. With degrees used, the equation applied is the one with 360 degrees for one revolution. Use n as 3, and k values are 0, 1, and 2. For the first root, k is taken as 0. Z1 is the cube root of 1 times cosine of 90 plus 360 times 0 over 3 plus I sine of 90 plus 360 times 0 upon 3. The second term is zeroed out, so Z1 is just 1 cosine of 90 upon 3 plus I sine of 90 over 3. This is simplified further as 1 cosine of 30 plus I sine of 30 degrees. Convert this into rectangular form by multiplying 1 with cosine 30 degrees and get root of 3 over 2 plus 1 times sine 30 degrees and get half of I. The second complex root uses k as 1, plugged into the equation to make the cube root of 1 times cosine of 90 plus 360 times 1 over 3 plus I sine of 90 plus 360 times 1 upon 3. The additional revolution then makes the argument 450 degrees. So the second complex root is 1 times cosine of 150 plus I sine of 150 degrees. In Cartesian form, 1 cosine 150 degrees gives negative root of 3 over 2, and 1 sine of 150 degrees is 1/2 times I. The last complex root applied, k equal to 2 into the equation, making the new argument as 90 times 360 times 2 or 810 degrees. The equation is then simplified into 1 cosine of 270 plus I sine of 270 degrees. In rectangular form, 1 cosine of 270 is 0, and 1 sine of 270 is negative 1 with I. So Z3 is taken as negative I. With the next example of finding the roots for negative 27, z cubed is interpreted as negative 27 plus 0y. The modulus is the root of negative 27 squared plus 0 squared, which turns out as positive 27. Placing the complex number into the Cartesian plane, the vector shown as a horizontal arrow pointing to negative 27. Thus, the argument is then seen as 180 degrees. By using the equation in degrees, we take n as 3 and k are 0, 1, and 2. For the first complex root, k is equal to 0. That would make the equation cube root of 27 cosine of 180 plus 360 times 0 upon 3 plus I sine of 180 plus 360 times 0 all upon 3, where the second terms become 0. So the shortened equation is 3 cosine of 180 degrees over 3 plus I sine of 180 upon 3. This can then be written as 3 cosine of 60 plus I sine of 60 degrees. In rectangular form, this turns into 3/2 plus 3 root of 3 over 2 of I. For the second complex root, k is 1, making the equation the cube root of 27 times cosine of 180 plus 360 times 1 upon 3 plus I sine of 180 plus 360 times 1 all over 3. The argument is then taken as 180 plus 360 or 540 degrees. The equation then turns into 3 cosine of 180 plus I sine of 180 degrees. In rectangular form, 3 cosine of 180 gives negative 3, and 3 sine of 180 is 0. So Z2 is just negative 3. The third complex root uses k as 2. Place this into the equation to have the cube root of 27 times CIS of 180 plus 360 times 2 all upon 3. The argument is then added to make 900 degrees. So the third complex root is 3 cosine of 300 plus I sine of 300 degrees. In rectangular form, we get 3/2 minus 3 root of 3 over 2 times I.